In the last video, we looked at thread state using the main thread. We just left off after creating a custom subclass of our own that extended the java.lang.thread class. In this video, I'm going to execute the code I included in that class as a concurrent thread to the main thread. To do this, I'll first create an instance of it in the main class's main method. I'll call it custom thread, and I'll just use the noargs constructor to create a new instance. To run this thread concurrently, I call start on the variable instance, so custom thread.start. If you're paying attention, you might be asking, why am I executing start and not the run method that I created and overrode? That's a really good question. I'll explain why in just a bit, but first I want to execute this code as I've got it set up here. You can see from the output, as it's running, the number 1 is printed every half second. The main thread didn't exit until this thread completed. But how do I really know that this thread is running concurrently to the main thread? I'll test this by setting up another for loop for the main thread that will do something similar. This time, I'll loop for 3 iterations. I'll print a 0 for this main thread instead of a 1 for each iteration. Again, I need a try-catch to catch an interrupted exception. Now, this time, I want to show you another way to make a thread sleep. I can use an enum, time unit, and one of its values, which are all units of time. In other words, I'm not limited to just specifying milliseconds. I can specify any unit on this enum, so I can use nanoseconds, seconds, minutes, hours, and so on. In this case, I'll use seconds and pass 1 to that, so the thread will sleep for 1 second. This code calls thread.sleep under the covers and does the math to figure out how many milliseconds this is. And like I did for my custom thread, I'll print the stack trace if I get this exception. If I run this code now, notice the numbers 0 and 1 are printed out and they're alternating. This is a pretty good sign that the threads really are running concurrently, each doing its own thing and not waiting on each other. Now, I wanted to get back to the earlier question, why did I call the start method and not the run method? Let's see what happens if I do call run, so I'll change custom thread.start to custom thread.run. If I run the code this way, I'll get all 5 ones printed first, followed by the 3 zeros. When you execute the run method, it gets done synchronously in the current thread. The main thread runs this method like any other method on a class and waits for it to complete before continuing with its next tasks. There's a big difference between calling run and start. If you execute the run method, it's executed synchronously by the running thread it's invoked from. If you want your code to be run asynchronously, you must call the start method. I'll revert that last change so that it's executing the start method again. I'm going to control-click on that start method to see what the Java code is really doing inside this method. You can see the method has a synchronized modifier. I haven't covered this yet, but I'll be coming back to this special keyword later in this section. Notice next that there's some code to add this thread to a group, and then it calls this .start0. I'll control-click on that method to follow the trail. Here, I've got a method declaration with no body, it's private, and it's got this native keyword. What is this telling me? The native modifier indicates that this method's source code isn't written in Java. It's written in another language, such as C or C++. The code in this example is part of a native library, such as a DLL file. When would you want to use a native library method? The reasons to do this include when you want to access system-level functionality that's platform-specific, when you want to interface with hardware, or when you want to optimize performance for tasks that might be computationally intensive. In truth, creating a thread is an expensive operation. Later, we'll talk about why you'd want to use thread pools to reduce the work needed to create a thread on your operating system. In this case, the Java code is handing off to a native library to do the thread creation here to both access system-level functionality and to optimize performance. Okay, so hopefully you understand now that calling the run method directly from your thread instance isn't creating a new thread at all, it's simply executing that code directly. The start method is the method that will do the work of creating the new thread, and on that new thread, executing the code in your run method. Now, let's look at the second way to create a new thread, which is by implementing the runnable interface. It's important to recognize that runnable is a functional interface. Its functional method, or its single access method, SAM, is the run method. This is really important because this means that anywhere you see a runnable type, it's a target for a Lambda expression. Not only that, but you can have any class implement the runnable interface and then pass it to the thread constructor to run asynchronously. I'll insert this next code before the last for loop in the main method. This is where I have the main thread printing as 0 3 times. I want this code to run concurrently, both with my custom thread as well as the main thread, so I'll insert my code before this final for loop. I'll create a runnable variable using a Lambda expression, and I'll call that my runnable. Don't forget that the code I write here represents the code that goes in the run method of runnable. In this code, I'll define the task I want the thread to perform when it gets executed. You can think of this as your thread's task. I'll add a for loop in my Lambda expression. This time I'll do 8 iterations. I'll print the number 2 for my second concurrent thread on each iteration. I know I need a try block, so I'll set it up. Here, I use the milliseconds value on time unit and pass 250. Whether you use thread sleep method or one of these enum values like I've done here and call it sleep method, this is really up to you. For myself, I kind of like that this method is self-documenting. As usual, I'll catch any interrupted exception and print information about it. That's the Lambda expression containing the code I want to run, but how do I actually use it in a thread? Well, I first need to create a new thread instance and pass this Lambda expression, which is ultimately just a runnable, to the thread constructor that takes a runnable as an argument. I'll call new thread, passing my runnable variable to that constructor. And again, I can simply call the start method on this new thread instance. Now, if I run this code, I can see all 3 threads running at the same time. The main thread prints the zeros out, the custom thread is printing ones, and this last thread, created using a runnable Lambda expression, is printing 2s. Okay, so what's really the difference between these two approaches? Let's take a minute to review the differences between these 2 thread creation methodologies on a couple of slides. This slide demonstrates extending the thread class. The new subclass overrides the thread's run method to provide the concurrent thread's task. To use this thread, you create a new instance of your subclass with a no-argument constructor and execute the start method on that instance. The advantages of this methodology are that you have more control over the thread's behavior and properties. You can access the thread's methods and fields directly from your subclass. You can also create a new thread for each task. The disadvantages of this way of thread creation are that you can only extend one class in Java, so your subclass can't extend any other classes. In other words, a subclass of thread is external to any domain-specific hierarchy that you might also want for this subclass. Another disadvantage is your class is tightly coupled to the thread class, which may make it difficult to maintain. Besides extending the thread class, you can create threads by implementing the runnable interface. This method allows any class to implement runnable, meaning any class at all can be used in a thread. This class is passed to the thread constructor that accepts a runnable. You can also pass an anonymous class, Lambda expression, or a method reference to this constructor to create an instance of a thread. You again call start on the new thread instance to execute the code asynchronously. The advantages here are that you can extend any class and still implement runnable. This gives you more flexibility in your design. Your class, if you create a class, is loosely coupled to the thread class, which makes it easier to maintain. You can use anonymous classes, Lambda expressions, or method references to very quickly describe thread behavior. The disadvantages, in my opinion, are few, but you do have less control over the thread's behavior and properties. In other words, you can't access the threads methods and fields directly from the run method. Now that you've seen how to create threads and how to fire them up asynchronously, it's time to talk about a bit of thread management. In the next video, I'll cover how to interrupt a running thread, as well as how to create dependencies among the running threads. I'll see you in that next video.